Of course, you can write the same thing by dividing by LPS to get this form. Those two forms are the same. Let's think about two extreme cases. When LPS is so much lower than KD, and this value becomes 0, and the whole thing becomes close to 0. What it means is that when we have negligible LPS, there will be no reaction anyway. But if LPS is much, much higher than KD, then this one will dominate and becomes 0, and the rate will just become Vmax. This means that the formation of active TLR will happen in a maximum rate. What about the concentration in between? So we just talked about this extreme and this extreme, and it will go like that. And just halfway, we have KD. And around here, things can be linearized. So we can do the linearization and see that, in fact, around this range, active TLR will increase linearly. So we do a little bit of linearization, supposing that LPS is KD plus some small value, and you just plug into the LPS to get this, and then you divide the whole thing with KD to get this. So we can use the approximation, the power series approximation that Einstein famously used for derivation of E equals to mc squared. If you have 1 plus some small number to the power of n, is approximately 1 plus n epsilon. Now, if n equals minus 1, such that we have 1 plus epsilon here, and is approximately, well, equals 1 plus epsilon to the power of minus 1 equals 1 minus epsilon. So you can do that approximation here to get exactly that. And we do the same thing that we did here to bring it up. Then you get to see that active TLR will be linearly proportional to the LPS concentration scaled by KD. Finally, we come down to this, the intracellular signaling kinetics. We discussed all the details of ligand binding on the receptor, and as a result, we'll have an active TLR. And this active TLR will work as a catalyzer for this reaction from I kappa B, the inhibitor of NF kappa B, NF kappa B complex. Basically, I kappa B is called inhibitor because when it makes a complex with NF kappa B, this complex is inactive. But when they are dissociated into I kappa B and NF kappa B, I kappa B will fall into the natural course of degradation, so it'll just go away. But the cytosolic part of NF kappa B will translocate into the nucleus, and this portion we call NF kappa B nucleus portion, and it will bind to the promoter of some gene that it eventually express some kind of inflammatory molecule secreted by the T cell. We assume quasi-equilibrium once again. So when this NF kappa B, I kappa B complex binds to the active TLR, actually this is not active TLR per se. It should be some kind of intermediate molecule between the TLR, active TLR, and this complex. And when they are together, there goes a forward reaction, predominantly forward reaction, toward the dissociation into cytosolic NF-kappa B and inhibitor of kappa B and active TLR fluid again. And if we assume this quasi-equilibrium, we can write down the same equation that we already discussed using Michaelis-Menten kinetics. Like that. So we can describe the cytosolic portion of NF-kappa B, its rate of change per time, as a concentration ratio of active TLR with respect to some kind of KD for it. Let's call it KT. And if you look at the degradation of I kappa B, when it becomes degraded, it will not come back to its original form. So this is definitely one way, right? So you can write down equation for I kappa B. It will have the same synthesis form that comes from this part. It will be the same rate as the kappa B cytosolic portion. But then it has a degradation form which is proportional to its own concentration multiplied by some kind of linear rate. So as long as this degradation is not an enzymatic process, we can write down like this. Finally, the cytosolic NF-kappa B will come into the nucleus, process called translocation, and becomes a nuclear NF-kappa B. And we can move back and forth, right? So there will be nucleus toward nucleus forward rate and toward cytosolic backward rate. So we can just write down. This is the easiest part, I guess. So from the forward rate will be proportional to the concentration in the cytosol. If we have a lot, it'll move more. So we can write down like that. And from the nucleus, it may get out of the, move out into the cytosol, and you can write down like that. So we have all equations that we need up to the signaling, intracellular signaling. We have a part for the LPS binding on the TLR, and it'll create active TLR, and with active TLR there will be dissociation of the NF-kappa B, I kappa B complex, and the cytosolic NF-kappa B concentration rate will be like this, and then I kappa B like this. Finally, some of those NF-kappa B will go into the nucleus, and the rate can be written like that. Now, all you have to do is to solve this equation. And to solve this equation, you must have some ideas of the parameter values. And we discussed a little bit about that for the TLR LPS. And you can carry on with the same argument. You can search the literature, and there are actually the concentration estimations of concentrations of cytosolic NF-kappa B and cytosolic I kappa B, as well as the nucleus NF-kappa B. What's left? So next class, we'll talk about the transcription, translation, and transmitter release, all the remaining part. Plus, the important, we'll think about the ballpark realistic parameter range so that a simulation work can be done at home.